Hello, my name is Marco Fariñas and I'm a PhD student in Kaisaleti's research group at the Norwegian University of Science and Technology. I am presenting a poster on BooLEVARD, a Python package to count paths toward node activation and inhibition in Boolean models. Therefore, let's start with the definition of Boolean models. A Boolean model consists of a network of interacting nodes, each representing a biological entity that can exist in one of two states, active, 1, or inactive, 0. Dynamics within Boolean models are brought by Boolean or logical equations, which are expressed as functions of binary variables using AND, OR, and NOT logical operators, and determine each variable's next state, on or off, on the current states of its regulators. A stable state is a network configuration of all on and off nodes that once reached, the model's Boolean equations live exactly as is, so the system stays stuck in that pattern. Whereas a stable state is a fixed on-off configuration, BooLEVARD quantifies each node's influence by counting all acyclic regulatory paths leading to it. As a result, BooLEVARD bridges the gap between the discrete and continuous worlds of signal transduction. As I mentioned earlier, BooLEVARD is available as a Python package designed to compute the number of paths leading to node activation or inactivation in Boolean models. BooLEVARD's input is a Boolean model in the standard Boolean format. In this example, we see a Boolean model integrated by 7 nodes and 10 interactions, of which 2 are negative and 8 are positive. BooLEVARD operates in a stable state-wise fashion, and the user can choose whether to run it across all stable states reached by the model or to select the specific stable states. The first step is to read the local states of each node within the stable state. For example, here A is off and B is on. And next, BooLEVARD transforms the Boolean equations of active nodes and the negated Boolean equations of inactive nodes into the canonical disjunctive functions, namely CDNFs and CNDNFs, respectively. A DNF is a Boolean equation expressed as disjunctions of conjunctions. If we take a look to this example, we can see that the Boolean equation of E is not A and either C or D, and its respective CDNF is either not A and C or not A and D. Therefore, DNFs help us to see independent ways a given node has to get active or inactive. Next step involves to retrieve the drivers. The conjunctive blocks within a DNF capture all the independent ways a node has to activate or inactivate itself. But since here we're constraining with the stable state, we filter out those ways that do not evaluate to true. Following the same example, in node E we have two potential ways, not A and C, and not A and D. Whereas in this stable state, the first one evaluates to false, the second one is true. Therefore, its driver in this stable state is A and D. Also, since we got the CDNFs and CNDNFs, we do not care anymore about negated or non-negated literals. We just get the unsigned node to construct the drivers. Last step before path counting includes drivers reduction. Take a look to node D. If we see here, it is only regulated by B. Therefore, it can be omitted and the logic will be completely conserved. This allows to increase the speed of path calculation performed by BooLEVARD. Finally, in this example, we're counting the Boolean paths leading to G. And we observe that we have two independent paths leading to G. G is activated by E and F, E is activated by A and B, and F is activated by C and B. C is activated by A in the first path or by B in the second. Finally, the poster includes a use case in which we studied invasiveness and apoptotic self-fade decisions in a model of cancer metastasis developed by Cohen et al. We performed several perturbations in the model and plotted the distributions of ones and zeros transformed to path counts in this upper panel. As one can observe, we have more granularity, and below we plotted the relationship between apoptosis, as apoptosis resistance, and evasion. Although a correlation was observed when using ones and zeros, implementation of BooLEVARD further reinforced this association.